Hello, welcome everyone, and thank you for joining us at this episode of Spectroscopy in Action, our live webinar series. My name is Paula, I'm the Marketing Account Lead at Edinburgh Instruments, and today I will be joined by Georgios, our Product Specialist, who will be discussing dual mode transient absorption spectroscopy. Today, Georgios will be giving us an in-depth look at the LP980 and its dual mode capabilities for studying excited state dynamics. He will discuss the fundamentals of transient absorption spectroscopy, explain how iCCD and PMT detectors operate, and guide you through the intuitive software that controls this. Demonstration of data acquisition will show just how easily the LP980 delivers high-quality transient absorption spectra and traces. At the end, we'll have a Q&A session, so you'll have the chance to ask any questions you might have. Hope you enjoy the webinar. I'll now pass over to Georgios to get started.
So, good morning, everyone. I hope you can hear me well. Thank you, Paula, for the introduction. So today I'm going to present you nice things about transient absorption spectroscopy and how you can use this technique by using one of our spectrometers, the LP980. So the first part of the webinar focuses on the fundamentals of the technique. We will see how how transient absorption works and how to interpret the transient absorption spectra. Then we will move to the description of the data acquisition on the LP980 using two detectors: an intensified charge coupled device, an iCCD, and the PMT. And then a few pre-recorded measurement examples will be shown using the LP's software, showcasing how easy it is to use the instrument with either detector. And then I will close the presentation by allowing you to question your questions. So firstly, let's dive into the transient absorption fundamentals. Study or monitor a photochemical or photophysical process, we must first initiate it with light. And on absorption of a photon, a hypothetical molecule, like this one over here, can be promoted to a higher energy level. But when the molecule or atom or species returns to its ground state, there are multiple candidate pathways, such as those shown here. Needless to mention that apart from luminescence, the rest of the processes over here are non-radiative. So the radiated processes can be studied using photoluminescence spectroscopy, a fairly straightforward technique that has been analyzed in our previous webinar, and that I highly recommend to watch it on YouTube on our channel. The rest of the processes appearing here do not include the emission of light, so during relaxation, and therefore photoluminescence spectroscopy would be meaningless. So transient absorption is an alternative technique suitable for studying the dynamics of the excited species. But how transient absorption works? So transient absorption essentially is a pump probe technique, meaning it involves two beams, an intense light source, such as a laser, to excite the sample under study. And then we've got a weaker in intensity probe beam to monitor the dynamics induced by the pump. So more precisely, while measuring transient absorption in the LP980, firstly, a very fast first measurement is acquired with the laser shutter closed so that the probe background can be acquired. So that's the probe beam from a xenon lamp that can be detected. And through this measurement is essentially it's the absorbance of the probe beam as a function of time. And what we get in the software is seen over here in the figure. So it's the absorbance as a function of time. Essentially, what a transient absorption spectrometry does when the laser shutter now is open is to detect small changes in this probe background if any transient species exists. So then we need the pump beam, the second beam. That's the laser source that excites our species. And um, what essentially happens is that the laser shutter closes and the lifetime of a radiative or a non-radiative transient species is probed from their absorption as a function of time. So we are talking about resolutions from nanoseconds to seconds in the LP980. So now let's look at an example which is quite common in nanosecond transient absorption. And this slide shows the mechanism of photoluminescence spectroscopy before moving on to transient absorption. Molecules initially in the ground state are getting excited to the first state, the S1, by an excitation beam going through the sample. The sample then can relax back to its ground state, emitting fluorescence, that is in the nanosecond time regime, or it can move through inter-system crossing to a triplet state. And from the triplet state, it relaxes to the ground state, by emitting a light at longer time scale. That's the process called phosphorescence. In a photoluminescence spectrometer, fluorescence and phosphorescence are detected at a right angle from excitation to avoid any interference and filtered out using a monochromator. We can have continuous excitation and scan the monochromator to obtain an emission spectrum, or we can excite with a short pulse and study the decay as a function of time, obtaining the photoluminescence lifetime of the sample. So as we discussed before, the issue with one issue with photoluminescence is that the excited states can relax to the ground state non-radiatively. So if it happens, then transient absorption is the alternative technique to detect these and study these excited states. And note that we compare probe absorption versus pump and probe absorption, the excited state. So let's look what happens in a pump probe setup. We start with a population of molecules, mostly in the ground state. We excite with a high energy laser pulse. We need a high concentration of our initial sample, roughly between 0.2 or 0.4.5 optical density at the excitation wavelength, and a high photon flux of excitation to achieve a good concentration of excited state species. After some time, the excited population relaxes through inter-system crossing, as we mentioned before, and this will create a triplet population. So while the system relaxes, we probe it with a white light pulse, and that's the absorption that takes place. So the absorption in the singlet manifold takes place in a fast femtosecond timescales. If there is absorption in the triplet manifold, it takes place in the range of nanoseconds to milliseconds. And this is actually what we typically detect in the LP980. And this results in a positive component in the delta OD spectrum that we measure. There are also negative components in delta OD, which come from the ground state bleach. The pump pulse has depleted the population in the ground state, so its absorbance has decreased, which results in a negative change in the OD. And remember that the delta OD, as we will see in the next slide, is actually the subtraction of the excited state minus the ground state. So just like in photoluminescence, we can also look at delta OD as a function of time to get the relaxation dynamics of the sample. So let's look how the calculations of the delta OD take place. So in this, that's the equation that is used in order to calculate the delta OD. And the numerator represents the ground state absorption, which is obtained by measuring the probe background through the sample. That's what we saw before. The denominator is the absorption of the excited state that is obtained when both pump and probe pass through the sample. And the delta OD is simply a subtraction of the probe-only absorption from the pump probe absorption. This means that we typically end with some negative components, as we discussed before, in the region where the ground state absorbs. And also over here, we have also we can also see that we've got multiple TA spectra, and this is that we typically get by using the iCCD, and we will see later on that essentially this is a delay map. So we can acquire TA spectra at different time delays. So now let's move on to the unique feature of the LP980, which is the two modes of acquisition by incorporating two detectors. You can have a kinetic detector, like a single point PMT or a photodiode, to record the kinetic traces at a single wavelength. And we've got multiple options covering different ranges. Or you can have a spectral detector, like an iCCD, to acquire the full spectrum of your sample in just one single laser shot. The main capabilities of the LP980 can be seen here. The standard PMT detector enables time-resolved absorption and emission measurements from 10 nanoseconds to seconds. Gated absorption and emission spectra can be obtained with an intensified camera, the iCCD. And you can also add a photon counting upgrade for more sensitive measurements of phosphorescence decays. Essentially, when I mentioned here about gated emission spectra, I'm talking about laser-induced fluorescence. So the LP980 is also capable of measuring LIF. We will see later on how to do that. So in order to move forward, it's worth mentioning how an iCCD camera works in the LP980. So the iCCD, as we mentioned before, is used for time-resolved spectral measurements. So photons enter the camera and strike the photocathode, releasing photon electrons. These are then multiplied through a micro-channel plate, which provides significant gain. And that's actually the key feature of the LP980 and exactly this microchannel plate. So the microchannel plate is responsible for the fast gating. So the MCP the microchannel plate can be turned on and off within nanoseconds, allowing us to isolate specific time windows after excitation. The gate width can be moved from 3 nanoseconds if we go with the fast option, or starting from 7 nanoseconds if we go with the standard option on the LP980, and this can go up to seconds. So the amplified electrons then hit a phosphor screen, converting the signal back into visible light. And finally, the light is detected by a CCD sensor and is digitized, giving us a precise gated spectrum of the transient species at a defined delay time. So this is how the LP monochromator looks like if we use the iCCD. As we mentioned, the iCCD is an array detector, and in this case, the aperture of the monochromator is relatively large, so the full spectrum can be imaged onto the iCCD at once. And we can obtain the full spectrum at the selected delay in just one laser shot. Also, what we can do is with the iCCD, we can acquire delayed spectra with respect to the pump pulse to obtain kinetic information. So if we only had the iCCD and we wanted to, to acquire kinetic information of our sample, we would have to acquire the TA spectra at different time delays. And this essentially is a 3D representation where the z-axis is time. So if we data slice the spectrum over here, essentially we get the decay of our sample. So that was for one detector of the LP980, the iCCD, and now let's move on to the PMT. How a PMT works. The PMT is essential for like the photocathode, releasing photoelectrons. So these are then accelerated through a series of diodes, where each stage multiplies them, resulting in signal amplification by a factor of around 10 million. And thanks to its nanosecond rise time, the PMT is ideal for capturing fast kinetics. Finally, the PMT outputs an analog voltage signal, which is directly to the oscilloscope. And this allows us to visualize and analyze the transient decay curve in real time. So if we had to use the PMT on the LP980, we would drive the beam through the PMT. And as we mentioned, the PMT is a single point detector, so it detects transient absorption at a single wavelength. And it transient absorption decay with high time resolution in a single laser shot. So what if we had only the PMT as an option and we wanted to obtain spectral information of our sample? What we would have to do is to measure the lifetime at different wavelengths. And as with the iCCD camera, that essentially is a 3D representation where the third dimension gives us information about the spectral data. So it's possible to acquire a transient absorption spectrum just by the PMT, but this will take a while. It's a time-consuming technique, and also it's not recommended when your sample is photosensitive, as it is quite possible that you end up by burning the sample. So the iCCD is ideal for acquiring spectral measurements. So now we can move on to how to use our software. And over here, I've got a recorded video of the LP980 software, and I'm going to show you how easy it is to acquire and transient absorption spectrum with just a single shot. So let's play. So just pause the video. So just to let you know that over here is the toolbar of the software, and these two buttons, the red buttons, refer to the measurements that can be done with the iCCD camera, and the blue buttons refer to the measurements that can be done with the that's the measurement if we wanted to get laser-induced fluorescence. So that's emission, and that is absorption. So I'm choosing absorption. I go to multiple to set the parameters. And from here, I can set the number of iterations, actually the laser shots that will be on the sample. I can choose different backgrounds. So it is recommended to acquire the Pro background for a meaningful delta of D calculation. And also, what is also possible to do is, assuming that our sample is highly fluorescent and we wanted to exclude it from our transient absorption spectrum, we can choose this fluorescence background, and then in the delta LB calculation, it will be subtracted. So we won't have any fluorescence interference in the transient absorption spectrum. I press apply and then start. So firstly, the LP gets the probe background, so that is with the laser shutter closed. And essentially, that's the result. So with just a single shot, we obtained the TA spectrum of our sample. This sample is a rose Bengal, and we used, I will show you later on, we used the laser at 355 nanometers. Also, I have the raw data over here that were used to calculate the delta LB. So, okay, I'm going to move to the next slide. So this is the result, sorry. So this is the result if I wanted to compare the singlet shot measurement with 10 shot with the 10 shots laser measurements. So you can see that the blue spectrum represents the singlet shot measurement, and the black graph represents the 10 shot. So this is just to show you how the signal to noise ratio might change from 1 iteration to 10. The sample that we used was a rose Bengal in acetonitrile. The light source that we used was a neodymium YAG laser at 350 nanometers. That's the third harmonic of the 1064 nanometers. And the repetition rate is 10 hertz. And the detector for these measurements is an iCCD. The gate delay was 0 seconds, so there was no delay between pump and probe. And the gate width, essentially the gate we open to get information, was 100 nanoseconds. So with the iCCD, I can also, as I showed you before, you can get delay maps, which is quite useful if you want to see the evolution of your transient absorption spectrum as a function of time. To do so, as before, I chose the absorption button and then moved to delay maps. And from here, I can set the spectral map setup. So I can have multiple groups of different delay maps, and over here I set the parameters of the map. So I start from 0 seconds. The stop is 15 nanoseconds, and a step size of 3 nanoseconds. I press OK, and then start. You can also see at the bottom over here the evolution of the measurements. So that's the total number of the spectra that will be acquired. And I can see in real time the probe background and the probe plus pump measurements at different time delays. And once the measurement is done, the delta LB calculation will be automatically done, and this is the results. This is the result. So essentially, what you see here is the evolution of the TA spectra of our rose Bengal sample, different time delays. This is quite useful when we have such samples, and you want to study the dynamics of your sample as a function of time. So the next slide regards the laser-induced fluorescence. So the LP980 is also capable, suitable to measure fluorescence. We've got a dedicated sample holder for leaf. In the case of leaf, you can set your sample even closer to the monochromator in order to increase your signal by 4 times. So let's see how to do that. Previously, if I wanted to measure the absorption TA spectra, I had to choose this button. Now for the emission, I'm moving to the next one. And as before, I set over here the parameters. I change to just a single shot, my measurement. I can change also the slit width of the monochromator. I change it to 0.1 because it's quite sensitive. And with just a single shot, that's the laser-induced fluorescence of rose bengal. And as with the delay maps of the transient absorption spectra, we can do similar thing with leaf. We can have the evolution of laser-induced fluorescence as a function of time. To do so, I go again to emission and delay map to set the parameters of the delay maps measurements. I select the ranges. I can also, from here, you can see that you have a selection of the time scale from nanoseconds to microseconds, milliseconds, and to seconds. So if I wanted to generate a new group of measurements, I would have to go over here, press update, and I would have a second group to set the parameters. And I can have as many groups as I want. I set the parameters as with a previous measurement with the absorption, and I press start. So that's the leaf at 0 time delay, leaf at 3 nanoseconds, 6 nanoseconds time delay, and 9 nanoseconds. And the final spectrum I get is at 15 nanoseconds time delay. So these measurements regard the iCCD. What if I wanted to measure PMT kinetic data? I'll show you how to do that. So with the iCCD camera, I get the information on the spectral measurements. I can see how our sample behaves in a single shot at all wavelengths. So if I wanted to measure the change of the delta LD at a specific wavelength and measure the dynamics, the kinetics at this specific wavelength, I would have to choose the PMT. So now I go onto these two buttons. I go to absorption for the PMT. I change the number of iterations to 20, and I'll show you how to do that. From here, essentially, these are the oscilloscope parameters. And from here, essentially, I change the parameters of the laser and the probe beam. I have chosen fluorescence background to be excluded, and I start the measurement. So that's the background of the probe on the PMT, what it ends. That's what I get with probe plus pump, and the blue one represents the fluorescence. And if I want to just move on to the last measurements, because this required 20 iterations, and that's the result I get. So that's how it looks like the decay of rose bengal at this wavelength, the 554. And the LP980 software allows me also to apply fit decay. So if I have to calculate the exponential fit, I go to data, exponential fit, tail fit analysis. And from here, I can set an initial guess of how much these species lasts. So set an initial guess of 200 nanoseconds, and I press OK, and then the software automatically calculates, performs the fitting and calculates the decay. So this one is 370 nanoseconds. So I just show you how easy it is to calculate the kinetics of your sample by using the PMT. So finally, as I'm approaching the end of this webinar, I would like to let you know that we will attending the ICP conference in Aachen mid-July. So if you're there, please visit us at our booth. I'll be there, and I'm happy to discuss with you all your questions you can have, and whatever we can do to facilitate your research. And thank you very much, and I'm open to any questions you may have.
Thanks, Georgios. I'll just check if we have any questions. So we've got a few actually. So what type of type of samples can be measured? Would you only be tied to be able to one type, for example, liquids or solids?
So with the LP980, you can able essentially whatever sample you want. You can measure liquids. So we've got a sample holder for liquids, the cuvette holder. You can measure thin films. We've got a dedicated sample holder for thin films. And also you can measure powders or films that are not that transparent. So we also have a sample holder for diffuse reflectance or quasi-collinear geometry that essentially are recommended for these types of measurements. And also we can measure samples in a gas form. So we've got dedicated sample holders for a variety of different samples.
Well, yeah, that's great. There are lots of options for whatever your research requires. And what light sources can be coupled to the LP980?
So we usually recommend neodymium YAG lasers. And so the repetition rate, the maximum repetition rate that the LP can use is 10 Hertz. So we usually have neodymium YAG lasers, but also you can integrate optical parametric oscillators so these devices allows you to tune your wavelength. So essentially, you can measure a variety of wavelengths from visible up to NIR. So these types of lasers can be integrated on the LP980.
Yeah, again, lots of options depending on your research. And the final question we have just now is, what are the main application domains?
So yeah, so that's a good question, because if we wanted to actually, a good idea would be to have the next TA webinar specifically focused on applications. So the first application that comes to mind, and it's quite popular, is photocatalysis. So if you wanted to study the dynamics of the species that takes place in a photocatalysis, you could need transient absorption measurements. Another one would be photodynamic therapy, which is also quite popular. In photodynamic therapy, you have you can measure the dynamics of the excited species that takes place in these processes. And also in photodynamic therapy, just because you have the generation of reactive oxygen, you can also measure singlet oxygen. So yeah, LP980 is also capable of measuring singlet oxygen. Other application that comes to mind, and it's popular, it's a bit complex. It calls triplet annihilator up conversion. Essentially, in this complex process, you've got multiple energy transfer between molecules in the triplet state. So transient absorption is the ideal technique for such measurement because these processes are not radiative. And with up conversion, essentially you convert a low energy photon into a high energetic photon. So for example, from the NIR to the visible. So everything that has to do with solar energy, for example, solar cells, the study of efficient OLEDs, can be based on up conversion. So transient absorption is essential for this kind of measurements.
Okay, great, thank you. Yeah, if that does sound like an interesting next webinar for transient absorption, so if you're interested in that, please let us know. We have another question here, one that I can actually answer, is will the webinar be uploaded or available somewhere? Yes, it will go on YouTube live, YouTube after the webinar. So you'll be able to watch it again or share it. And the other question is, how would one choose the gate widths and bandwidths and steps for the maps?
How are these can be done?
Yes.
So this can be done through the software. Can possibly show you again. So yeah. So here is how you set the parameters of the delay. You can either do it from here if you wanted to measure a delay map, or you could if you wanted to take just a single delayed measurement, you would have to go to camera over here, and there would be another tab that allows you to change the gate width and the delay. So it depends on what you want to do. If you wanted to have a delay map, the best way to do so is to go to this tab over here that is suitable for delay maps. Or if you want to go with just a single measurement at a specific time delay or a specific gate width, you would have to go to camera over here and set the parameters of your interest. And the other question, I think, has to do with the slit width, right? So then you would have to go to controller over here, and there would be another tab that allows you to change the slit width of the monochromator.
Thank you. I hope that answers your question. If not, you can email us and we can set up another chat for you if you've got anything specific about the software like that. I think that's all the questions that we have today.
Great.
So thank you, Georgios, for presenting, telling us all about dual mode transient absorption spectroscopy. As I said, the webinar will be published on YouTube for you to watch again, and you can share with colleagues that you might think who you might find this useful. We will also be continuing this series in August, so please make sure you're subscribed to our newsletter to be the first to find out about what's happening next. And you can also subscribe to our YouTube channel to see all of our latest videos. So finally, thank you for joining us. We hope you found this session helpful, and we will see you next time.